Well, welcome again, now that we have audio, to my talk about analyzing and improving performance of universal Windows apps. My name is Johan Laanstra. I am a software engineer on the Windows Next team at Microsoft. My slides are full of links to all kinds of background content, so I will publish them on my GitHub afterwards. So don't worry if you feel like you're missing anything. You can all click on all the links and find all the content that we will talk about today. You can find me on Twitter at @jplaanstra, or you can always email me at my Microsoft email. So like I said, I work on the Windows Next team. It's a team in Windows that works on the inbox apps. So all the applications that ship with Windows, like photos, maps, those are all taken care of by this organization. And my team specifically owns 3 simple utility apps: Voice Recorder, Alarms and Clock and Calculator. And for those apps, we have done some performance work in the last couple of releases together with the platform teams on how we can effectively measure and then find patterns in our performance and make sure that our performance gets better. So in this talk, we will go over the Performance 101 for universal Windows apps. Basically, a list of things that you as a developer should follow and should follow from the start, even if you're not immediately focused on measuring your performance. Those are the things that are the general best practices. Then we will look at the tools that are available to you in the Windows Performance Toolkit, and that will mostly happen through demos. So we'll talk about best practices, and then we'll dive into Windows Performance Toolkit and get familiar with what it shows and what you can do with it. So let's start with the Performance 101. It has been said 100 times or maybe even 1,000,000 times. The fastest code is the code that you don't run. That doesn't mean you shouldn't do anything. It means that you should try to, when your app starts, postpone the work that you want to do as long as possible. This can be examples like registering background tasks. Those are not crucial for your app to start, so you should probably try to postpone doing that as long as possible. And we'll see events in the app that are great to use for these kinds of things. Other things include setting up push notifications. And the other thing that a lot of teams and a lot of people do is they see performance as a thing that they look at the end. Let's say the last iteration before we ship, we'll check if the performance is great. And the recommendation is just to measure early, define your goals and targets early, and just make it part of feature development. A feature isn't done until it also has great performance. So I quickly want to talk about 5 categories of that affect your app's startup performance and performance in general. Keep the UI thread responsive. The UI thread is the thread that does the most work on the startup path. Optimize your Xaml. Xaml is the way you build a UI for a UWP app. So making sure that it is optimized and as efficient as possible will help your startup time and your general performance. The new thing with UWP is xBind. Well, we've had it for a couple of releases, but there are some great enhancements made to that in recent releases that give it an even better advantage over traditional binding. We want to minimize the work during startup, and we have specific techniques, like I said, to achieve that. And depending on the language that you use, like C++ or C#, there are language-specific recommendations that we will also quickly go over. So let's start with the UI thread. Things that are not required to do anything with the UI, you should put them on the background thread. You can get back to the background thread using dispatcher or run async. And in addition to run async, there is run idle async. Run idle async is basically a run async that has priority low, but its overload specifically allows you to check if there's additional work being put on the dispatcher while you do a long-running task. So while your long-running task is running, you can check on the event hours if there's additional work being done, and you can cancel your background work and continue and post it again on the idle dispatcher, and then you can continue your work when your UI thread becomes idle again. Now the links, those bullet points are all links, and if you click on them, you'll get more of the background info. For apps written in C#, synchronization context occurrent is preferred over core dispatcher or over an async. And that's because in apps with multiple windows, synchronization context occurrent will capture the context for the right window, while core dispatcher or async requires that you are already on the UI object, or you need to find somehow the view that you're associated with. And in apps with multiple views, that's not necessarily the main view. It can be a secondary view. And in C# you all have, of course, task.run to run work on the background thread. Now, the second thing I want to talk about is optimizing XAML. Every element that you put in XAML has a cost. So reducing element count is one of the most efficient ways of starting faster and having a more efficient UI. Try to reduce elements that don't produce any pixels, like panels, grids, a grid and a grid and a grid and a grid. If you can simplify it to just one grid, that will have slightly better performance. A single panel is in generally more efficient than multiple panels. A vertical stack panel with multiple horizontal stack panels is in general less efficient than when you use a grid and define rows and columns. I say in general, there are obviously exceptions, but in most cases that is the rule. Panels have border properties these days. You don't need to put a border in your template anymore. You can just define your borders on your panels and in that way save an unnecessary border. And try to use grid for overlapping UI. Grid has been optimized for overlapping UI compared to using alignment like margin and padding to put things on top of each other. And reducing element count especially helps in lists. In lists, every element will duplicate all the duplicate elements that you have in your templates. And there's additional information on MSDN later on this. We added a new feature called xload recently in XAML, which is similar to the load strategy. It allows you to tell XAML that this is part of your UI is not visible right now. We don't have to initialize it right now. We can defer that work until the point where we actually need it, and that will obviously help XAML rendering. UI virtualization has been mentioned like a lot. Basically, use a panel that supports it, like an item stack panel, and minimize your overdrawings, which means don't put a rectangle that is red on top of a rectangle that is yellow on top of a rectangle that is white, because it requires the framework to basically render three things, and they will all draw on top of each other. So it's partially waste. There is more information on the link on how you can find out how much overdrawing you have, because a little bit of overdrawing is unavoidable. One thing you should definitely avoid is layout updated. It's an event that gets raised a lot, and is often not, the work that people put in a layout updated event isn't required to be run that much. It's quite expensive. And what a lot of people used to do is they would retemplate the control just to change some colors in the Visual State Manager. So what the Xaml team did in a couple of releases ago, they defined resources for each of the colors that a template supports. So what you can do, instead of overriding the template, you can override specific brushes in the resource dictionary for your specific instance of your control, or for all the controls of that type in the whole app. And the link there also has more background info on this. In UWP, we added xBind, also called compiled bindings, and there are some other terms that it goes under. xBind has much less CPU and memory overhead. It doesn't depend on the data context. The data context is a property on framework element that is in some way special, in that its value inherits down the tree, and that makes it much more expensive. Like if you change it, there's an expensive propagation that propagates the data context down to all the other child elements unless the data context is specifically set there. And in recent releases, we added both event bindings and function bindings. A lot of people who are familiar with the MVVM pattern are generally people generally recommend to use iCommand. And we actually try to avoid iCommand and use as much as possible event bindings or event handlers that then call functions on the view model, and that is also makes operations that are async on the view model much easier to hook up and, for example, show temporarily a spinner or similar UI. The same applies to value converters. Value converters are ways in Xaml to transform one value to another type, and looking up a value converter and then calling the code that is, for most people, generally C# requires one operation to go through interop back into the framework, and then another interop operation to go back in the converter to actually run the code, besides just looking up the value converter in the resource dictionary. So with xBind, you can specify in your binding, you specify use this function to convert object X to object Y. And you can define the function in a value converters class, but it requires less interop and lookup, and it's generally faster. Now, to minimize work during startup, I already said defer the work as long as possible. Avoid loading a lot of DLLs, like especially reading DLLs where you might just use one class on your startup pod requires us loading the whole DLL. Loading less DLLs makes your startup time faster. What I've also seen, or what we've also seen, is people generally have an await before they call window occurrence will activate. And that basically means that if your await takes long for some kind of thread starvation reason on the system, and you don't call window occurrence to activate in time, the system will eventually kill your app if you don't call activate. So the recommendation is to postpone asynchronous work until the splash screen.dismissed event. That's the perfect event that indicates that your splash screen is done, you're now visible on the screen, now you can do all extra work. And if you really start fast, then with the fall creators update, we now allow you to opt out of the splash screen. So you can specify the optional parameter on your splash screen element in your Apex manifest, and basically opt into the splash screen. So what will happen is the system will start your app, and if you are visible in time, it will completely skip the splash screen. Another thing that used to be on by default in UWP is pre-launching. So what the system would do on launch, if the system was idle, pre-fetch certain apps into memory that you would frequently use. Now that caused issues. For example, some music apps would start playing music in the background without you having the app open. So the decision was made in the anniversary update to make this an optional thing. So an app has to specifically tell the system that it wants to opt in, and it can of course help the performance, or at least help how the performance looks of your app, because half of the app will be already preloaded in memory. Now on the language side, for both C# and C++, there are language-specific recommendations that can help the performance of your app. Please don't call gc.collect manually. It basically garbage collection heuristics are really good. Try to minimize manually garbage collecting. Like for debugging reasons, it's of course the exception. But gc.collect causes a garbage collection of all generations instantly, and it will just pause all the threads. And you basically have to wait until that is done before the threads can continue. The other thing that for C# applies is memory allocations, like less large memory allocations, or especially medium-term objects. They generally don't survive a generation 0, and therefore they will live longer, and your memory usage will be bigger. We prefer in general to either have short-lived objects or very long-lived objects when it comes to C#. and sometimes it's preferred to use managed types to avoid interrupt. So if you enumerate the list of notifications on the system that your app's at, if you constantly access that list, then you constantly get a copy of that list back that goes through the interrupt layer. And in those cases, it might be much more beneficial to just copy it into a managed list and then stay in the managed memory space instead of constantly going back. For C++, use the latest C++ toolset. There's a lot of compiler optimizations happening. There's a lot of work happening on modernizing the compiler and adding additional optimizations. There's no runtime or XAML dependency on RTTI, which is runtime type information for C++. So if you don't, there's no such thing in general as called reflection in C++. So if you don't need RTTI, disable it. The link has more info on how to turn it off. The PPL, which is basically the equivalent of task in C# or the parallel patterns library, is really heavy and is no longer actively being maintained. So the recommendation is to use co-await, which is a new C++ 20 feature that is currently available in the C++ compiler. And that ties in with the prefer standard C++ over CX, which CX is primarily there for the interrupt layer and not meant to be a general used language. We are actually working on a replacement for CX, which is called C++ WinRT, which is more standard C++ on top of the Windows runtime. Now, this link has much more information, and you can find it in the slide deck later. So now let's, during debugging and during development of your app, it's of course very handy to have the Visual Studio performance tools available. You can debug, you can see what's going on, you can do CPU memory analysis, but you might not always be able to attach a debugger and use Visual Studio for these things. You might have an app in the wild running on someone's machine, and there might be performance problems with it that you can't necessarily reproduce on your own machine. Or the Visual Studio tools might not be sufficient might not provide sufficient detail, or you might not have the correct information to find out what the problem is. In those cases, the Windows Performance Toolkit is very handy. It's a very powerful tool. We use it inside Microsoft a lot for our performance analysis. It basically consists of two things. There's the Windows Performance Recorder and the Windows Performance Analyzer. The Windows Performance Recorder specifically is the tool to use to capture a trace for a scenario you want to investigate. And you would then open the trace in the Windows Performance Analyzer, which is a special tool that you can use for analysis and really finding the root cause of what's going on. The specific reason that this is split up is because in general you take the trace on a different machine and you analyze it on. So which approach do we in general take for performance analysis? We identify that there is a problem. That's generally step one. My app starts really slow, or my app doesn't meet my target. Then we use WPR to capture a trace, and we'll see shortly how. Capture a trace of the scenario. It's preferable to make the trace as short as possible and really focus on a specific scenario so you don't have a lot of noise in the trace. And then we take that trace generally from a different machine. We put it on a fast dev machine and we analyze the trace in WPA. We want to determine what the cause of the problem is. Is it CPU? Is it disk? We're using too much memory? Is it a network bound problem? One of the things that is very important is to identify the UI thread, and we'll see how to do that soon. The UI thread is generally involved in a lot of these performance problems, so it's really nice to know which thread it is. And then WPA allows you to figure out what time is spent on what. Then we make the modifications and we go back to step one. So let's do that. Let's do some demoing. So I made an app in Visual Studio. And all it does is it fetches a bunch of Bing images. So I have 4 tabs. I have a cat tab, a dogs tab, a Microsoft tab, and a computers tab. And as you can see, the memory is is already at 700 megs and growing. And if I scroll a bit, it can go up, or I switch the tab, it goes up a little more. Oh, we're at 1 gig now, 2 gigs. Anyway, there are some problems with this app. It didn't really start fast. Has a high memory usage. The first thing we would do is we would take a trace. So we would say Windows Performance Recorder. Now the great thing about Windows Performance Recorder is it comes with the SDK. If you already have the SDK on your machine, you will have it. And the command line tool is ships with Windows in box. So any machine that runs Windows 10 will have Windows Performance Recorder on it. So there's no need for people to get binaries from somewhere or download some shady thing to get a trace. You can do this on any machine. So let's take a look at what this tool all has. So the thing here is that is a list of profiles. So we have the first level triage, which contains basic information of the system. You will generally always want to have that included. And then you can focus on specific resources if you'd like CPU, disk activity. And then there is a scenario analysis step. So since this is a Xaml app, we will use the Xaml app responsiveness analysis profile. So you can check that. Now on the right, we have performance scenario, detail level, and logging mode. Now performance scenario, you generally want to use general because we're not trying startup of the machine. The detail level indicates the amount of detail that WPR collects while running the trace. Now, why would you not always want to collect verbose? It's because sometimes you want to. That depends on the logging mode. So if you have use a memory, you have a limited amount of space and a buffer in memory to put all the data in that you're collecting. And in that case, it might be useful to have light to not run out of buffer space immediately. Now, I already took it, and then you press start, and then we'll record. Now I already took a trace because for demo purposes it is obviously preferable. It will trace all applications on the system. So we'll take a trace from the whole system. For the recording, the question was, how does it know which app it's going to collect information for? And the answer is it will collect it for all. So let me open the trace in WPA. It should be very quick. So I took this trace for the same app. I browsed a bunch of tabs. I took this on an ARM64 machine to get a less fast device than my dev machine. Now the first thing you'll see here on the left is the Graph Explorer. The Graph Explorer, basically all the information that is available in the trace, WPA will group that together in those categories. So you have computation, storage, memory, and the lines in the Graph Explorer will give you an indication of what kind of problem you're having. So we can see that computation is quite high, so we might have a CPU bound problem. And we'll also see some weird things going on in our memory graph. Well, we already saw in Visual Studio that there is definitely some memory problem here as well. So one thing we can do is we can take computation and drag it onto our analysis window. And of course it doesn't work the first time. There you go. And what we will see here is a list of all the processes that were running on the machine while we took this trace. So we can see CPU usage sampled, utilization by process. We don't care about stacks at this time. So these lines are basically showing the different processes on the machine, and the tooltip also gives additional context. So we can see that this purple line in this case is our TechDays performance app. So the first thing we want to do is make sure that nothing weird is happening on the machine while we took this trace. So we see a bunch of processes here. We see system, we see DWM. DWM is a process that runs on each machine and generally does work as part of the app. Like things like rendering and communication with the GPU is handled by DWM. And there is generally also some system activity which we could attribute to the app. Other processes are memory compression, MSMP engines, Windows Defender, Surface Host, and those are pretty low. WPR UI is our trace collection tool, Windows Performance Recorder. So there isn't really anything weird happening here. So this is a good trace for us to use. As you can see, both the graph and the table will kind of work together. So I selected system here, and in the graph you see bars on when the system is doing things. We can do the same for our TechDays performance app, and then you can see the different selection. And the same applies to if I decide to like select a time in the trace, you will see that the table automatically gets filtered, and you can see that TechDays performance is darker blue than the other running processes on the system, and that means that our app was more active during the time. Now we have our TechDays performance. We can right-click on it and say Filter to Selection. It basically removes all the noise from other processes on the system. It just gives us a focused view of our own app. We can select a part of the beginning of this trace and say Zoom, and specifically focus on this part of the trace. Now, what we see here is that for quite a while we have like constant CPU usage around 25%. Now this is an indication of a problem, because this machine is a quad core, and 25% CPU usage basically means that one core was busy 100%. So it might be the case that there's a thread here that was 100% using our CPU. Now, what we can do is we can drag in another CPU usage, like CPU usage attributed. And that is very useful because we can show that selection in one of the graphs applies to both of the graphs. So the selection, once you select a certain part of the timeline, that will apply to all the graphs in your analysis tab. Now, one thing that we want to do is we want to find what the UI thread is. So to do that, we will use a slightly different preset. We will check utilization by process and thread, and then we can have a rough guess that our thread 10.5.24 is the UI thread. And why am I saying that? Because that is the thread that does the most work. This is the startup part of our app. We know that our UI thread is probably the most busy thread, so it's a good assumption that this thread is therefore the UI thread. Now, we don't have to just assume this. We can check in WPA if that is actually the case by adding the thread name tab, and you will see that indeed 10.5.24 is the XAML UI thread. Now, a quick some more detail on what this gold bar means. So the gold bar is basically everything left of it indicates how we group our data, and then everything on the right means what are we going to show in the graph. So you might want to, sometimes when you enable an additional column, it shows up on the right and you want it on the left, and you can just drag it over and then it will group it. Now, let's add CPU attribute back. You can rename tabs, so you can give this a name, say My Analysis. And you can close that, and then you can save this as a profile. So you can export it and give it a name. Let's put it on the desktop, demo. And now the next time you get a new trace, you can just open the profile. It will open the exact same tabs that you had open with the exact same graphs that you dragged on it before. So you don't have to reset up your Windows Performance Analyzer every time you analyze a new trace. Now, you don't have to necessarily build your profiles yourself. We ship a profile that we use a lot for XAML app analysis. Basically, you click Browse Catalog and then you select XAML app responsiveness analysis.wpa profile. And when you open that, you will get a set of tabs that we have that are already predefined for you. And we'll let that load for a sec. So a couple of things that we can see here is one of the interesting graphs of this profile is the window in focus. So here we can see that during this time, our window was the app that was in the foreground. Now that means that it was after the splash screen was dismissed. So if you're specifically looking for your starter performance, then this is generally not the part that you would be interested in. You will be interested in application frame host, which is the one that is showing the splash screen. Now, one of the things we can look at is let's select this, filter to selection or zoom, and switch to the frame analysis tab. So here you can see some information about GPU, CPU usage attributed, and what we see here in GPU usage is what is considered in general a healthy GPU usage graph. There's some spikes. They are not high. That means that the GPU did some work, but not a crazy amount. For a Xaml app, that is generally what you would expect. Now, on the CPU usage attribute, we can see some more information on what the UI thread was doing. We can see that there is a pre-selected XAML UI thread CPU breakdown, which will automatically focus on what your UI thread was doing. And we can see here that there is some services updates, some frames. There's some image load happening, which would be expected because we loaded a lot of images. And we can see that all the way at the bottom, we have a couple of frames. Now, these frames allow us to exactly see what the UI was doing, what XAML was doing during this frame. So in frame 0, there was a XAML frame. In frame 1, these are mostly all XAML frames. In cases, that's because there wasn't a lot of UI for us on the screen yet. When there is, you will see things like measure, arrange, rendering, all kinds of these things. Now, how am I sure that this part was that I selected? Let's zoom out to. I zoomed in here, I guess. Yeah. How do we know that this was actually the time that our app was starting? Now, what you can do, let's go back to the code. You can add a trace. You can trace from your app. So basically what you would do is you would create either an event source in C# or use the logging channel APIs that we provide to you as part of UWP, and trace events at the critical points in your app that you are interested in or that you think there's problems with. And then you can instruct WPR to in addition to the system providers that it would collect information for, also collect the information from your own event source. Now, the way I did this in this app already, I create a logging channel called TechDays.demo, and I specify a GUID. And the GUID is the way that I can later, when I collect a trace, specify that I want to collect information for this GUID. If you don't specify a GUID, there is a predefined algorithm that is shared between both the logging channel and the event source APIs in .NET to derive a GUID from the name that you specify. Now, I have a method to log a message that will check if there is actually someone listening. We can skip expensive work if no one is actually listening to our events, and a start activity method. And the method start activity, the nice thing about an activity is that will produce both a start and a stop event when you stop the activity, and that way you can get like an area of information and know, okay, this is when when I started this method, this is when I ended this method, and see what the work was that was happening in the meantime. Now, I did this for the unlaunched, that is part of every UWP app. I created a load activity here by calling start activity with a predefined name, so I can find it back in WPA later. And then I do the work, and then in the end, I call stop activity with the same name. Now, if we go back to the trace and we create a new tab, we're going to drag generic events. And generic events contains the list of all the providers that that WPR collected information from. And as you can see here, our TechDays.demo provider is in the list. Now, how did we get there? Well, to do that, you have to create a WPRP profile. Documentation online with the links in the slides will show how to do that. Basically, what we do is we specify our event provider, and here we use the GUID that we saw before. And then we create a profile with a detail level, an ID, a logging mode. And we specify, please include this event provider. Now in WPR, in the UI, and on the command line, you can specify this profile. In the UI, you go to Add Profiles. I go to my desktop where this file is located. I open it. And under Custom Measurements, my custom defined profile will now show up and will now be included in the trace. So I can do the same thing like I did before. Start, run the scenario, stop, and then the trace you get will have the event provider in it. And in this trace, I have that indeed. So let's look at the onLaunch task name, which is the task name is basically coming from the string that I passed into my activity. So there will be a start and a stop under it. And that's pretty much all the information that is in there right now. I didn't add any additional values or fields. I will have a start and a stop. And as you can see, the start started at about 8.6 seconds till about 13.3. So now if we go back to our frame analysis, let's see, to my big picture, I can see that from about 8 till about 13, that was indeed the place where application frame host was in the foreground. So during the whole of our onLaunch method is the primary reason that our splash screen was visible, because of work we did in there. And you can see that I clearly violated one of the recommendations that I'm awaiting before I'm calling window.kernel activate. Now this is one of the things that we recommend you don't do. Call activate as soon as possible. Another thing that you can do is once you have a lot of these events, just browsing through the generic events class and finding out where all the, some of these providers have a lot, you can see they have a lot of markers. Windows allows you to create what is called a regions of interest file. Regions of interest file basically allows you to define start and stop markers and say, okay, I'm interested in these markers. Please show me bars for each of those. And one of the things that we have is a predefined set of regions of interest that you can see here. Let's drag that on here as well. Now, it created predefined regions of interest based on my specified activities. So you can see that I had some load images work in the beginning. I clicked on all the 4 tabs. The first one took longer, possibly because of additional classes being initialized in the first time. And you can see that there's clearly optimization possible here. First of all, I didn't in the beginning click on the second tabs, so it was loading all the images while I wasn't on the tab. And it's also loaded in serial here instead of in parallel. We could parallelize this. And then at the end, I refreshed one of the tabs, and you can see that there's another set of events for this. And you can see actually the string that I passed in that I loaded cats twice. Now the load pivots thing is the method that is initially called by onLaunched, and you can see that those bars are actually exactly overlapping. So you can see here that in the onLaunch I actually call load pivots, and load pivots has another activity with the load pivot string. And you can see here that that spans basically the whole of the time. Now there are additional regions of interest files that ship with WPR. You can find them in the documentation on what the events are that are shown in the standard regions of interest files. Now, let's say you're in the situation where you have a trace from 2 weeks ago that was great, where your performance was great, and now it's not so great anymore. What you can do with WPA is you can do a comparative analysis. So what I basically do, besides opening this one file, I will open a second one. And you can see that there's now 2 graph explorers here, one for the first trace and one for the second one. And I can combine graphs from both of the traces in my views right now. But one of the most powerful things that you can do with this, and you can, by the way, recognize that all these tabs are for trace 1 because they have a blue one. There's both a color and a number indication. And you can create a new comparative analysis window and say like, okay, trace 1 is my baseline, trace 2 is my comparison trace where things are not going so well. And then you can continue. And what this will do, all the graphs that you now drag onto this comparative analysis view, so let's do a CPU graph. CPU is sampled. This will show not necessarily what is actually happening on the system. It will show a diff between the first trace and the second trace. So all the numbers here, a negative number means that it was in the first trace but is no longer in the second trace. It was in the baseline and is no longer in the problematic trace. And positive numbers mean that it was in the problematic trace but not in the baseline. So as you can see, the scenario that I ran obviously didn't match between those 2 traces. So you'll see that TechDays performance shows up high here and it shows up low here, and that has to do with the time selection and the fact that I ran different apps on different machines, and that's why it doesn't match. But this is really powerful to find what is the difference between that time and the problematic time, the good state and the bad state. Now let's go back to the presentation. We did the demo. So if you want to know more, there's a very short URL that you can use, aka.ms/perftools. It has all the information about WPR and WPA, and much more than I could possibly cover in this talk. And there's a lot more and a lot more powerful graphs that you can use to diagnose all kinds of different issues. Are there any questions? The question is if the performance recorder only records the UI parts or also network parts. It also records network calls, so you can actually see the different URLs that the calls are being made to. And to do that, I will drag the possibly under communications, and I'm gonna switch just to trace 1. And you can see a whole bunch of URLs that were sent here, and you can see that the amount of bytes received, the amount of bytes sent, and this also works together with all the other selections. So you can focus on a certain part of the trace and then see which network calls were made in there. Does that answer your question? Great, thanks. Any other questions? So the question is that the app in this case doesn't necessarily come back completely from sleep mode. You can take a you can take a trace for that case and then see what is happening. And one thing I didn't specifically show because it is quite hard to demo is the fact that you can show stacks of the code that is running during a certain timeline. And to do that, you need symbols. So what you can do is you can configure your symbols here under configure symbols path, and you can point it to the location on your machine where the symbols for your app are, and then it can show much more details about the code that was actually running, and then you can see why it didn't do what it should do, and it can help you that way in diagnosing the issue. All right. Well, thanks for coming, and if you have any questions later, you can always email. The slides for this presentation will be uploaded to my GitHub, so you can click on all the links and get all the extra info if you need it. Well, thanks for coming.